Hello guys, so in this video we are going to see what actually happens with the least squares. So in the previous video we saw that what happens when your number of equations are greater than the number of variables. You could lead with a situation like this where you have no solution. So you can see that there are three lines over here, but there is no one common point of intersection, so that solves all the three equations simultaneously. So no solution is possible for this particular case. So what we actually try to do is we try to find a point somewhere such that we will not get the actual solution. So we want some xy such that we won't get the actual solution, but we get a solution which is closest to all of them. So for an example, if suppose I take this xy point as this, suppose, so where this is say 0.5 and this is also 0.5. So we had these three equations: x plus y is equal to 1, x is equal to y, and x is equal to 1. And suppose that I take this point 0.5 comma 0.5. So when I put 0.5 comma 0.5 over here, so 0.5 plus 0.5, this will give me 1. So this is satisfying this equation. Similarly, 0.5 minus 0.5 will give me 0. It is satisfying this condition also, but it will not satisfy here. So this will become 0.5 plus 0 is equal to 1. So this will be basically 0.5. So my actual vector that I wanted, my actual b was 101. So this was my actual b that I wanted, 101. But what am I getting is, I'm getting 1 1, and I'm getting 0.5 over here. Oh sorry, 10. So here this is satisfied. So this is giving me 0, x minus y is giving me 0. So please concentrate on these values. So over here I got 1, so that is 1. Over here I got 0, so this is 0, and this is 0.5, so I'm getting 0.5. So this was actually what I wanted. I wanted 101, but what am I getting is, I'm getting is 1 0 and 0.5. So this is what I'm getting. So there is some error that is over here. So I want a solution. I want an x comma y somewhere such that I can get the minimum error. So here if you see my error is say 0.5. If some, so we need some distance metric also. So we'll see how we deal with those things. So I guess the idea is clear that suppose I want some point, some xy, such that I get some vector, that is some values which is closest to the actual value. So that is my task. So let's see how we can do that. Okay, so this was for three equations. We could generalize that for n equations. So here I have given a general least squares case where I am taking n equations. So now you have n equations and you have two variables, suppose. So let's see how can we deal with this. So we'll have a matrix like this, which will be some n cross 2 matrix. So like this, A was 3 cross 2. This is 3 cross 2 because I have 3 equations. So now I have n equations, so it is n cross 2 and 2 variables. So the number of variables are number of columns, number of equations are number of rows. This is my x comma y, that is equal to some b1 b2 up till bn. So now this is the case that I have, ax is equal to b. That is what I have. So I have given this x bold. So this bold x basically means that vector x comma y. So this bold x is this vector x comma y, and this bold b is this vector b1 b2 up till bn. So that is what we have seen. So now what does the least square solution say? So the least square solution says that don't give me this x, because I know I can never have this kind of x because no solution is possible. So what am I saying is, give me some x cap, some approximation of x which will give you some b cap. So this is that some approximated value. So like over here this thing is our b cap. This is some approximation of this b. It is not equal to b, you can see over here, but some approximation of b. And x cap is this 0.5 comma 0.5. So this 0.5 comma 0.5, some point which is not the actual x comma y which I wanted. I wanted a point which gives me actually this, but this is not possible, as you can see from the graph. So I want some x cap y cap which can minimize the error. So I want this when I do this minus this, or whatever, this should be the closest to the actual solution that I want. So that is my case. So I'll define an error over here. So that is what I'm saying, that so you should have some measure of how will you define the distance between the two, how much are these two far. That is what you will have to define. So what one can do is you can just minus this and take the square. So that is what is the least square solution. So for example, so here I have taken b cap minus b the whole square. So that basically means I had this b cap over here. So this is my b cap that I've, so 10.5 suppose. So this is an example, minus I actual b is what is this 101. So when I minus both of these, I get 0, 0 and 0.5. So basic element wise minus. So this is, you see, you get a vector over here, 0, 0, 0.5. This is a vector. So now what I'm doing is I'm taking the square norm of this. So the square norm basically tells you just square each elements in the vector and add it. So 0 square plus 0 square plus 0.5 square. So which gives you an error of 0.25. So this is 0, and when you equate this, you get 0.25, right? So that means I will say that the difference between these two, or the error between these two, is nothing but 0.25. So that is what I mean by least square loss or least square error. What am I doing is I'm just minusing both of the vectors that I got, and I'm just taking the least, so I'm just taking the square. So that is square solution. So I just squared and took out what was the error. Now I want the least square. I want a particular x value which will give me this minimum error. So this is 0.25. this was just random, but I don't know which point. It could be that suppose this point would give me a more less error. So that is what I want to find out. So that is the task of least squares. So I have this error over here. So what I did is basically here I had this equation ax cap is equal to b cap. So I'm just substituting this b cap as ax cap. That's all I'm doing. So now I have ax cap minus b the whole square. So basically just substituting this value over here, and this is what I'm getting. So now I want to minimize e. I want a minimum value of e. So what I can do is, so this thing can be written like this. So it is like whenever you have a square where a is a vector. So let me not take a. So say suppose I have some p square where p is some vector. So this I can write as p transpose into p. So this is basic linear algebra. So from linear algebra we know that we can do this. Similarly, this is the a square, this is this p square, so p square. So I can write it as p transpose p. This is the same meaning. So this is what I can write. Now what am I doing is I can put this transpose inside. So when I put the transpose inside, so what happens is this will get the transpose and this will get the transpose. And you know that when transpose comes inside multiplication, it changes the order. So over here I had ax cap. Now when transpose goes in, I get x cap transpose into a transpose. This is also basic linear algebra thing. Minus I am getting b transpose. So this is one thing, and this is the same. Now I am multiplying normal multiplication. So this gets multiplied by this and gives you this. This into this gives you this. Then this into this will give you this. Then this into this will give you this. And this into this will give you this. So basic multiplication. And then what we see is these both things are actually the same thing. So let us just verify it quickly. So now say I have a particular case. So let us continue with the same example that I was taking. So say there is this x cap, y cap. So I'm just recreating this thing over here. So this is x cap transpose. So my x cap, so let me write it over here, suppose. So x cap is nothing but this vector x, small x cap y cap. Oh, please understand, this is a vector x. So yeah, so this is a vector x and it has two components x and y. Like this case, this was a vector x and this has two components x and y. Similarly, x cap y cap. So now what is this? This is x transpose. So x transpose will look like this. When this is x transpose will look like this. Then I have A. So let me take the same A matrix that I have taken over here. So this is my A matrix. So this is 1 1 1 1 minus 1 0. So that is A. Oh sorry, there was this transpose over here. Oh, let me cut this. So I have x cap y cap and then there is A transpose. So this is A. So if this is A, then this becomes A transpose, right? And then there is this B. So B is nothing but actual B, the B, right? So the actual B. So that is over here. So let us just quickly multiply this and see what we get. So let us first multiply these two. So we have x plus y as the first element. So I have x cap plus y cap, my first element, plus x cap minus y cap. So so this becomes my second element. This is my first element, then the second element. So the second element is x cap minus y cap. This is the second element of a matrix. Please understand, this is first element, second element, then x and 0. So the third element is x cap. So this is what we have, and that is multiplied with this 1 0 1 matrix. So please understand, I just went up. So this is multiplied with this. Now what will happen is this will get multiplied with this, this will get multiplied with this, this will get multiplied with this. So I get x cap plus y cap plus, now this is multiplied with 0, so that goes away, and this x cap. So this is what I get. So the answer of this whole thing is nothing but this thing. Now what we'll do is we'll take this particular thing. So now this is B transpose A x cap. So this was my B. Now if I do 1 0 1, this is B transpose, right? Now I have A. So A is nothing but 1 1 1, 1 minus 1 0. So this is A, and I have x. So this is my x. So please understand, this was this thing and this thing is over here. Yeah. So let us again just multiply this. So let me just keep this like this, and I'm multiplying this. So x plus y, x cap plus y cap, then second x cap plus minus y, x cap minus y, then I have x cap. So this is what I get. Now multiplying this, so I get x cap plus y cap, x cap plus y cap. This multiplies with 0, and then there is x cap. So you see, both of these solutions are the same. So either you do this or you do this, any which ways. So this and this, both of these are the same thing. So since they are the same thing, I can write this as 2 times say x cap A transpose B, because both are the same thing, you can see over here. So I have just written that. So this both are just the same, so I can have this. So this thing just becomes minus 2 times x cap A transpose B. So that is what I have. Now what we are going to do is, since we need minimum, so the basic rule for getting minimum in the whole maths class is just to take the derivative and equate it to 0. So we are going to take a derivative of E with respect to this x vector. Please understand that x cap is a vector, you can see. Yeah, this is x cap, x bar, y bar. So we are taking and E is a scalar. We saw over here that whatever error we have is a scalar value. So error is a scalar value and this is a vector. So we are basically taking a derivative of a scalar with respect to vector. So by simple linear algebra calculus, you can understand that the derivative of this particular thing is this. So in simple case, the derivative of x p x, say this, so d by dx cap of this thing is nothing but 2 times p into x. So this is what we have, the first derivative. So this is one thing that we are going to use over here. So A transpose A can be seen as a matrix, and it will be always a square matrix. That is also an important thing. So even if A is a rectangular matrix, you can see A is a rectangular matrix over here, but then A transpose A will always be a square matrix. So there is this A transpose A that we have. So that is a square matrix, and this P is also a square matrix, please note that. So this thing can be so this is a matrix that is P, so that is what we have over here, 2px. So that is the derivative. Minus I had this both addition as like this, so this was what I have, and the derivative of this is just this x will go away. So this x will go away and you get this thing. So I hope things are clear over here, the derivatives and story. So the derivative of this thing is just x will go, and the derivative of this is this. So this, when we equate it to 0, that is the thing that we do, equate the derivatives to 0. So equating it to 0, then taking this over here, you get this, and you can cut the 2's because it is just a scalar. And now what I'm doing is, now this is a matrix, I can just take the inverse of this matrix, the matrix over here, I just take the inverse over here, and this is the solution of x cap. So this is how I get x cap. So by this I have a basic formula. So this is the formula for least squares. So the least square solution, or the least square formula. So if I have any equation like this, ax is equal to b, any equation like this, so I can find the answer, that I can find an x which is closest to this particular equation by this formula, the basic simple formula like that we have over here. So let's see the application. So we saw the homogeneous equations in my previous lecture. So we saw image registration. So we saw image registration over here, and we saw these different equations that we had. So this was the affine case. So if suppose you have not, if in case you have not seen this video, so it doesn't matter, it is just that we have a lot of equations over here, and if you want to see this video, you can just click this link over here, you'll be taken to the video. So it is just that we have all these equations over here, we converted this to the matrix form. So this is the matrix form that it looks. So this has now got converted into the form of so this is like b is equal to ax. So by using this basic formula of least squares, where x is nothing but this formula, and here b is this is a, and this is x. So we can find out the x that we wanted, the parameters that we wanted for this particular transformation, and you can transform the image. So that is what we can do, and the same thing you can do for homography. So in homography also you have these many equations, and these are the different parameters that you have. So that was about least squares. So I hope you understood. So that's all for this video. Thank you so much for watching. Thank you.